Swayam Prabha. Digital India. Educated India.
Good morning. So in this class, we'll talk about introduction to mass transfer operations. Okay, so as you know, in chemical engineering, we take a set of raw materials and we do reaction and then make some useful products. And these products can be fertilizers, pharma, or specialty chemicals, and many other things. So if you look at this entire operation of going from raw material to reaction to final product, the raw material or the products, they are not in pure forms. The raw materials are available as a mixture of compounds. We may not need all of them, so we need only some particular raw material. Okay. Similarly, the product stream also will not be completely pure product that you want to synthesize. It will be mixed with many unwanted compounds. This is because the reaction as such will involve many side reactions or unwanted reactions. Thereby, the product stream will also have mixture of compounds, including your desired compounds as well as undesired compounds. So, therefore, we are basically in a position to change the composition of a fluid mixture, okay, whether it is in the raw material or in the product stream. So when I say change the composition, what I mean by that is changing or enriching one of the compound over the other. Okay, so this can be said to be separation or purification. So in terms of raw material as well as product quality, the separation becomes a very important process, and mass transfer operation is one where we actually achieve this particular objective. Okay. So if you look at the chemical process industry, much of the times the cost is involved in the separation of equipment is quite high. The cost involved in the separation equipment design is quite high. So if you want to look at high pure compounds, if you want to make high purity compounds, there is a proportional increase in the cost involved. So because you have to work with the economics of the process as well, so designing a optimal separation process equipment is very much important, okay, because it's tied up to the economics directly. If you have to give an example, sulfuric acid, for instance, is quite cheap because its raw material sulfur is pretty much available in pure form in nature. On the other hand, uranium could be very expensive because naturally uranium is not available as a pure form. It is available as a mixture of compounds at a very low concentration, so you have to enrich uranium. This enriching process is what adds to the cost of the final compound cost. So therefore, we have to appreciate the need for purification and the cost involved in such purifications. So now, so having talked about this importance of separation in relation to purity and cost, so what are mass transfer operations? So we can actually define mass transfer operation as a transfer of a solute from one phase to another. Okay, so mass transfer operations, so I'm going to call this as MTO. Okay, subsequently, so this is basically characterized by a transfer of a solute from one phase to another at a molecular scale. So a very simple example could be you spill some water in the floor, okay, and then after some time if you see, this water would have evaporated. Okay, so what really happens here is very close to the water surface, the vapor pressure is defined by the room temperature, whereas the air in the ambience is dry, let's say. Then the difference between the partial pressure and vapor pressure between the liquid and the gas drives the evaporation of liquid water to the air surface. And then once the water molecule actually goes to the air phase and the air gets flown away, and then more and more water can actually evaporate. So after some time all this water gets evaporated. So this is a very simple example to illustrate how a mass transfer can actually happen at a day-to-day life. Now when we look at this mass transfer operation as such, first we try to classify them, and then we study each one of them as per. So the classification of, if I have to say, classification of MTO. So there are basically 4 classes broadly defined. Again, this classification is not very unique, it is actually of convenience. So you could say that direct contact of 2 immiscible phases. This is one class, one category. Then you have phases separated by a membrane. Or you could have a direct contact of two miscible phases. And for use of surface phenomena. So of this, in each class we will talk about, so we'll broadly classify this mass transfer operation to these 4 classes. The first one is a direct contact. When I say direct contact, I mean physically they are in contact of 2 immiscible phases, and then phases separated by a membrane. So use a membrane to separate 2 phases. Sometimes there are processes where the 2 miscible phases are actually in contact. They are basically a mixture. And the last one, which is which uses kind of surface phenomena or interfacial phenomena to effect separations. So of this, if I take the first class A, so here when we say direct contact of 2 immiscible phases, we often think about, so let me write this. So matter exists in 3 different phases: gas, liquid and solid. So of these 3 phases, if you want to look at a pair of combinations, you have 6 possibilities, right? You have got gas, this one particular 2-phase system, gas, liquid, gas, solid, liquid, solid and solid. So we got 6 possible combination of pair of phases. So here we are demanding that the 2 phases should be immiscible. By this requirement, we cannot have gas because most of the gases are actually miscible. Okay, so you cannot have gas mixture which are immiscible. So this choice is not relevant. Similarly, the solid is of importance, but not to chemical engineering, but this particular separation is usually done in metallurgy and material science. So we will not deal with this either. Okay, so that means we are basically left with 4 combinations: gas solid, gas liquid, liquid and liquid solid. So these are the 4 different types of processes that we are going to consider. Much of our MTO operation are going to be in these 4 combinations. Okay, for example, if we take the first one being gas liquid, so within this gas liquid 2 immiscible phase in direct contact, under this there are many MTOs, there are many mass transfer operations. For example, you can have a separation that involves all the compounds present in both phases. Okay, all the compounds present in both phases. So what are the what I mean by both phases here? Gas and liquid. Okay, we are talking about gas and liquid, and you have a mixture of multi-component system. I already mentioned that we are interested in changing the composition of the phases. Okay, so that means there is going to be a multi-component mixture in both gas and liquid. So in this particular case, we have all the compounds, all the solute in both gas as well as in liquid. Okay, so in this case, we use what is called distillation or fractionation. So fractionation or distillation is a mass transfer operation in which all the components exist in both phases, meaning in gas and liquid. So here the gas phase is typically created. So you take a liquid mixture, heat it, you get the gas phase, or you take a gas and then you cool and then you get a liquid. So the gas and liquid I'm talking about in this particular case are actually generated by liquid to gas or gas to liquid by simply applying heat. Okay, so here in this particular case, all the components are existing in both phases. Let me give an example. Let's take a liquid mixture of acetone and water. Okay, so this is a liquid mixture containing acetone plus water, and let us say X naught is the mole fraction of acetone in the mixture, in the liquid mixture. Now what I'm going to do, I'm going to apply some heat and then partially vaporize the mixture. Okay, not completely but partly. So then I will end up in a two-phase system. I will have a liquid here and a vapor here. In this particular case, the vapor will still have a mixture of acetone plus water. The remaining liquid will also contain acetone and water. Okay, so let us say the composition of acetone in this liquid is XR. In the vapor phase, let's say the composition of acetone is Y star. Okay, we use X for mole fraction in the liquid phase, Y as a mole fraction in a vapor phase, so that we can distinguish between two different phases. X is used for liquid phase, Y is used for gas phase. Here we are talking about a binary mixture. If I know the mole fraction of acetone, I know the mole fraction of water. Okay, so there is no need to use two mole fractions, one mole fraction is enough. So then what we do, we separate this particular vapor mixture. Okay, isolate them, so you get only a vapor here, and then you cool this. You cool this vapor mixture, condense it, you're going to get a liquid mixture again, right? This is going to be liquid after cooling, which again contains acetone plus water. What would be the mole fraction of acetone in this liquid? Is my question clear? So I have produced some amount of vapor and I'm physically separate them into two. Okay, vapor is separated and then the liquid is separated. I take the vapor and I cool it such a way that the entire vapor is now condensed into a liquid. Basically I am getting an acetone water mixture. What would be the composition? What would be the mole fraction of acetone in the condensed liquid mixture? Should be the same as Y star. So now, why are we doing this? What we have done, we have taken a liquid mixture, partly vaporize them, separate the vapor and liquid, and then condense the vapor back to liquid form. Now the question is, would this XD and X naught be same or different? If you have an engineer at home who is not a chemical engineer, pose this question. Okay, most likely you will get an answer that these two composition will be the same. But for chemical engineers, we know that is not the case, because the acetone and water they have a different boiling point, they have different vapor pressure, they have different volatility. So when you created a vapor here, this would actually have a much richer acetone than water. Okay, therefore after you do this operation, you will see your x d will be much larger than x naught, and xr will be leaner. So in the residual liquid after vaporization, this would have a leaner acetone, whereas the vapor that you condensed into liquid would have a higher mole fraction. So what we have done is, by simply vaporizing partly, separating the mixture and condensing back, we have actually effected some amount of separation of acetone rich and acetone lean mixtures. Okay, so this is what we call as a distillation. Now if you do this repeatedly, if I take this mixture again, I do one more vaporization level, if I separate them, and you continuously, you actually can keep on doing this multiple times and to try to reach a much richer acetone liquid, starting from a acetone water mixture. So this is a very simple principle that we can use in distillation. So this kind of process is what called distillation or fractionation. Now within this gas liquid, so let us underline this. So this is very, very important mass transfer operation. Next we will move on to another case where still we are talking about gas liquid. Unlike in distillation where all the components are there in both phases, you can have a gas liquid system where there's only one component that is common in both phases. Okay, a single component, single compound or single component common in both phases. An example could be, think about air plus ammonia mixture in contact with water. In this case, ammonia is more soluble in water than air. So ammonia will transfer from air to water. Okay, very little amount of water may evaporate back into a air phase, or maybe some amount of air which consists of oxygen, nitrogen can also dissolve in water. However, compared to the solubility of ammonia, solubility of oxygen, nitrogen is very less. So you can fairly assume that in this particular problem, only ammonia exists in liquid and gas. Water vapor is not present in the air mixture, and air is not present in water liquid. Okay, so you still have gas mixture that contains air plus ammonia, liquid contains water plus some ammonia solubilized. So here the common compound is only ammonia. Okay, so this is what I mean by a single component common in both phases, gas and liquid, and we call this as absorption or gas absorption. Now here I'm talking about transfer of solute from gas to a liquid, that's called gas absorption. You can also think about the reverse. You could also have a compound transferred from liquid to gas, just the opposite of the transfer. Okay, so when the solute goes from gas to liquid, we call this as absorption. If this compound goes from liquid to gas phase, we call this as desorption or stripping. Stripping and desorption are equivalent terms. So obviously these two operations cannot happen at the same temperature. So typically absorption happens at low temperature and stripping or desorption happens at a higher temperature. When you change the temperature, the equilibrium curve also changes. That's why this transfer of back and forth is possible. Okay, given a temperature, only one would be possible. Either absorption can happen or desorption can happen, not both. Okay, now the third possibility is the liquid can be a pure species. In the case of absorption, the liquid contains water plus solute, water and ammonia. Okay, But you can have a situation where the liquid will be always a pure compound, but the gas can have a mixture. Okay, for example, like I said before, take water and air mixture. Water gets evaporated into air. Okay, so the gas will have a mixture of air and water, but the liquid will be pure water because oxygen or nitrogen is not dissolving in water. And such a process we call it as a humidification. So air in contact with water. So this is what we call as a humidification. You can also have the reverse process. Okay, so that means you can have a moist air, hot, and then you contact it with water, cold water. Water vapor can actually go from gas phase to a liquid phase. That is called dehumidification. Okay, just opposite trend. So dehumidification is one where water transfers from gas to liquid, and the liquid here is pure water. Okay, the solute as well as the liquid, both are actually pure species. So in summary, if I have to think about the gas liquid system, two immiscible phases, we have distillation, absorption, or its counterpart desorption. Then we have humidification and its counterpart dehumidification. So these are very common gas liquid operations involving two immiscible phases. Yeah. The next combination is gas liquid is done and then gas solid. So under this category we have drying, where if you have a moist solid, okay, moistened with the volatile liquid, is in contact with the dry air, then this volatile liquid will escape from the solid into the gas. Okay, very simple example is drying of your clothes. Okay, we have a solid material moistened with water, and then you contact it with the ambient air, and water evaporates from the solid to a gas phase. Okay, so that is called drying. So solute transfers from solid to gas. Another example could be drying of filter cakes, drying of wood material. Okay, so there are many industrial processes that are involved in drying of solids. Okay, so then we have adsorption. In this case, we have a gas mixture, and then we contact with a solid, and one of the compound can actually transfer from solid to gas. An example could be take for example air plus water mixture, and you contact this with the let's say silica, activated silica. So water will actually transfer, water will get adsorbed on the surface of activated silica. After the operation is done, the air will be pure from water moisture. Okay, so activated silica is a very good adsorbent for absorbing moisture. Okay, so this process is called adsorption. Sometimes you may have more than one compound, more than one component in the gas, and the adsorbent can actually adsorb different solutes to different extent. Okay, for example, if you have a propane and propylene in a gas mixture, and let's say you contact with an activated carbon, and you will see that at equilibrium the activated carbon will have different surface concentration of propane and propylene, because the surface has different affinity to different solutes. So then we talk about fractional adsorption. So when you contact a mixture of propane and propylene with activated carbon, and activated carbon will absorb propane and propylene to different extent. Okay, so this is something we call as fractional absorption. Fractional absorption. So as far as gas solid is concerned, these are the two most important separation. Okay, drying and adsorption. And next we move to liquid and liquid combination. So this liquid involves a contact of two immiscible liquids together, and there will be one component that will transport across the two immiscible liquids. Okay. For example, if you take acetone plus water, and then you contact this to CCl4, carbon tetrachloride, what will happen is carbon tetrachloride and water, they are actually immiscible phases. Okay, it will phase separate into two liquids, one containing CCl4, other one containing water. Whereas acetone will partition between water to CCl4. Okay, so at the end of the separation, you will still have acetone in both phases, but it won't be at equal concentration. It will have a different partitioning. The acetone gets partitioned between two different insoluble liquid phases. So this is something we call it as liquid extraction. Then we have liquid and solid. In the liquid and solid case, again you can have adsorption. You can have a compound in the liquid that adsorb to the solid adsorbent. So that is called, example could be something like if you have sugar solution containing some impurities, okay, that gives this brownish color. If you want to remove that, you treat this sugar solution with the activated carbon, and this impurity can be adsorbed to the activated carbon, and what ends with is that you will get a purified sugar solution. Okay, so adsorption is one such. Okay, and again note that we already talked about adsorption in the case of gas solid. Okay, so adsorption can happen either in a gas solid mode or in liquid solid mode. Okay, so solid is common here. The other phase can be either liquid or gas. Again, the mechanism is that the solute will have to adsorb onto the surface or inner pores of the solid. Okay, so that is one example. Then we have something called leaching. In leaching, what happens is that it's kind of reverse. The solute actually transfers from the solid to a liquid. Okay, an example can be, let's say you want to extract oil from cotton seed. So oil is present in the solid phase, solid matrix, and use a solvent like hexane to extract the oil from solid to liquid. Okay, so that's called leaching. It's basically the reverse of adsorption. In adsorption, the component goes from liquid to solid. The reverse is leaching. Okay, there are many examples. So cottonseed oil from extracting with hexane, or sometimes gold is leached using a cyanide solution, again from a solid to a liquid phase. So these are some of the examples. And you also have other things like a crystallization, for example. In crystallization, you have a mother liquor, and then you cool it or vaporize the solvent, supersaturate the solution, and then you create a new phase, which is a solid phase. So in this case, you are actually creating a new solid phase. Initially, you start with the liquid phase. By doing some thermal process, you actually convert part of the liquid into a solid by nucleation and growth, and you create a solid phase. And that solid phase will be in coexistence or in equilibrium with the mother liquor or the liquid here. So that is called crystallization and zone refining. These are all related concepts. So basically, so these are all some of the important things we have to, we'll keep referring to: this drying, adsorption, then we have liquid extraction, adsorption, and leaching. So these are the things you have to keep in mind to understand what is the common characteristic of transfer, how many phases are involved, which way the transfer is happening, because that is important. And so this is all about the first class I was mentioning, where we talked about direct contact of two immiscible phases. We talked about gas liquid, gas solid, liquid liquid, and liquid solid. Okay, the other two, gas gas and solid solid, we are not going to discuss about. Okay, so now the second is about the phases separated by membranes. So in this case, we will not be discussing. So class B is direct. Phases separated by a membrane. So here the role of membrane is to separate two phases, okay, away from each other, and then if any solute has to go from one phase to the other phase, it has to go through the membrane. Okay, so that mechanism has to be diffusion. Okay, so there is no bulk hydrodynamic flow, so it has to, so it's basically acting as a barrier for solute transport. Okay, and example can be you have effusion. So in effusion, what happens is you have a gas mixture, and then you expose this gas mixture to a microporous membrane, and the membrane will allow solutes based on its molecular weight. Okay, so maybe the lesser molecular weight will easily transport across the membrane, and after the separation is over, you are left with two chambers. One will be rich in low molecular weight, another one will be rich in higher molecular weight. Okay, this is a gas diffusion, gas effusion method. Then we have something called permeation. In permeation, the membrane is actually non-porous. Membrane is non-porous. So in this case, what will happen? The solute will have different solubility in the membrane. If I have a component A and B, one of the component will be more soluble in the membrane. So first it gets solubilized in the membrane, then the other side of the membrane evaporates. Okay, for example, if I take ethanol water mixture and then treat it with this membrane, ethanol will be more soluble in the membrane than water. Okay, so first the ethanol kind of solubilizes in the membrane, and the other side ethanol evaporates into the gas phase. Okay, so this is called permeation. Then we have dialysis. So dialysis is a very common term again. So in this case, what happens is that you have a dialysis bag in which you can have the solvent, solute, and another solute which may be of higher size, larger in size. Okay, so in this case, the membrane will allow only the solute and the solvent to transport. The bigger molecule will be kept inside. Okay, this is a very important technique to separate large molecules like proteins or DNA or larger colloidal particles from solutes. Okay, then we have reverse osmosis and osmosis. This is also something very familiar to you. So in osmosis, again you have a membrane. Okay, so you got a solute plus solvent. So osmosis is one. If you separate pure solvent by a membrane, the other side containing a solute and solvent, the solvent will actually try to go through this membrane and then dilute the this particular phase. This is osmosis. This happens because of osmotic pressure difference between the two phases. Now reverse osmosis is the opposite. You apply a pressure in this side so that you can push the solvent from this side to this side. Okay, that should reverse the osmosis. That's what's called reverse osmosis. This is very important in terms of desalination, purifying water from salt water. Okay, where you apply pressure and then water is actually transported from salt rich to pure water. Okay, so whatever you have reverse osmosis system in your home is actually employs this kind of a membrane. So this is pretty much the classes. As far as the class C and D are concerned, that is direct contact of miscible phases or surface phenomena, they are not very common. These are typically used in isotope separations and nuclear engineering. And surface phenomena is very important, but it is not that common compared to these things that we are talking about. But In our research, at least, we use some of the surface phenomena to do a lot of transport phenomena by surfaces. So if you're interested, we can talk about this later. But as far as this particular course is concerned, we have only the two classes, that is the first class A, that is direct contact of two immiscible phases. Within that, we have gas liquid, gas solid, liquid liquid, liquid solid. Okay. Under this, we already saw distillation, absorption, desorption, humidification, dehumidification, drying, adsorption, leaching, crystallization, and so on. So, okay. So so these are all the kind of any broad, like I said in the beginning, these are not very unique way of defining mass transfer operation. This is one of the ways. Different textbooks happen to classify them differently. This particular classification is discussed in Treball, which is a textbook I am following for this course. Under the gas, liquid operations, distillation, absorption and its counterpart desorption, humidification, and its counterpart dehumidification, and under gas solid there is drying, adsorption, its counterpart desorption, or we don't talk about desorption here, so just adsorption, and you can have an extension of this as fractional adsorption. And then under liquid systems there is this extraction. Under liquid solid, so there is leaching, crystallization, and adsorption. So we looked at the characteristic of these mass transfer operations depending upon the nature of solute transport, whether the components are present in all the. So these are different types of mass transfer operations. So when we think about purification or separation, mass transfer operation is not the only method. Okay, there are other methods too. For example, we have mass transfer operations, some of which we just now looked into it. Sometimes we can also do separation based on mechanical separations, just mechanical operation itself, which we call this is just MO. And some separation is possible with chemical reaction engineering. So we call it as CRE approach. So the separation or purification of a species from a mixture can happen by any of these possible methods. So as a chemical engineer, we have to make a choice of which method to go after. Okay. So to give an example, let's consider a cases where both MTO and MO, that is mass transfer operations as well as mechanical operations, both could be possible to enhance the separation or purification. Okay. So let's take an example. Let's say you want to separate a mineral from its ore. We have got two choices. One is we can do a leaching with a solvent, which is a mass transfer operation, or we can do what is called this froth flotation, which is purely a mechanical operation. So we have a choice of either using leaching as a mass transfer operation or froth flotation as a mechanical operation. So we can choose one among these two. Another example. Let's say you want to extract a vegetable oil from a seed. So here again we have an option of leaching with the solvent, which is a mass transfer operation, or we can do what is called this cold press, which is a mechanical operation. So we have got two choices here. Another example. Let's say you have a vapor mixture, a vapor to be separated from a gas mixture. So here we have multiple choices. We can either do gas adsorption using an adsorbent, solid adsorbent, or we can do a gas absorption using a solvent, or we could simply condense the vapor into a liquid. So by removing heat, you can supersaturate, and then the vapor can condense into a liquid. Okay, so simple cooling or condensation. So which is more like a mechanical operation, whereas these are all mass transfer operations. It is not necessary that we have to use either MTO or MO operations. Sometimes we can have combinations also. Okay, very simple example is if you look at how we wash our clothes in a washing machine. So after washing is done, there is a centrifuge that spins off the cloth, wet cloth, to remove most of the excess water. After that you take it up and then you dry it in the open air. So here we have achieved two separations. One is a centrifugation, which is a mechanical operation, followed by a drying, which is a mass transfer operation. Similarly, if you take this example of vegetable oil extracted from seed, you can first do a cold press, extract most of the oil from the seed, and then follow that by a leaching operations. So it is also okay to have a combination of mass transfer operation and mechanical operation. Again, example, washing of clothes involves centrifugation plus drying. So this is a mass transfer operation, this is a mechanical operation. Similarly, the vegetable oil extraction can have cold pressing first, followed by leaching with a solvent. So here we are looking at choices between a mass transfer operation and a mechanical operation. Okay, like I said, CRE is also, chemical reaction approach is also another way of separating. Okay, so let's talk about the choice between mass transfer operations and chemical reaction engineering approach. Okay, again let's have an example. Let's have you have a liquid mixture of ethanol and water. Okay, so let's say you want to purify one of the compounds. So here the choice is, we could do distillation, which is a mass transfer operation, or you could actually treat this mixture with a lime. Okay, lime is calcium oxide. it readily reacts with water and produces calcium hydroxide, whereas ethanol will not react with lime or calcium oxide. So if we contact the liquid mixture of ethanol water with lime, which is basically calcium oxide, this can produce calcium hydroxide, or called slaked lime. Okay, and ethanol can be separated out. So here there is a chemical reaction that is involved to separate one of the compounds, in this case water. Okay. Another example is, let's say you have H2S, hydrogen sulfide, which is a gas that's very pungent and that needs to be removed from a air mixture. Okay. So here the options we have is, we can do a gas absorption. We can take a solvent and then wash it with this mixture, and then H2S can be separated, which is a absorption process, which is typically a mass transfer operation. The other choice is, we could actually react this with ferric oxide. With the ferric oxide, the hydrogen sulfide actually reacts and forms iron sulfide. So it chemically transforms from H2S gas to a iron sulfide compound. Okay, so therefore you can remove sulfur or H2S from the gas mixture. So this is a chemical reaction engineering approach. So if you look at this mass transfer operation and chemical reaction engineering, you will see one particular difference, that whenever there is a reaction involved, the solute undergoes some chemical transformation. It is not in original state anymore. In this case, water is now converted into some hydroxide forms. So here the hydrogen sulfide compound is actually converted into an iron sulfide form. So chemical nature of the compound is changed when you do reaction. So that is something you have to keep in mind when you think about separations, whether the solute needs to retain its character, its identity, or you're okay to change its identity or its chemical composition. So these are the choices we have to make. Now, these two examples, that is, we are looking at either mass transfer operation or mechanical operation. This is one class. Another one is mass transfer operation versus a chemical reaction engineering approach. So now, after this, if you look at only mass transfer operation, within that also we have choices to make. For separating a particular compound, there may be many possible mass transfer operation itself. Okay, so choices among MTO itself. So this is also another choice we have to make. For a given compound or mixture of compounds, there is no one single mass transfer operation that is applicable. There is a range of operations that are possible. Okay, again we will take an example. Let's say you want to separate a mixture of oxygen and nitrogen, purely from a mass transfer operation point of view. So the options we have is, we can do what is called this adsorption. So that means we treat this gas mixture with an adsorbent, solid adsorbent, which has a preferential adsorption of one compound over the other. Okay, so you can think of a molecular sieve or adsorbent that will selectively adsorb only oxygen or nitrogen, okay, leaving behind the other compound. So this is adsorption. The other option is, we can do what is called this gaseous effusion, which is basically a membrane-based mass transfer operation. So it is a very porous membrane, and it allows only a molecule of a particular size. So when you have oxygen and nitrogen, one of the compound will be preferentially passed through the membrane over the other. So this is also mass transfer operation. So we have a choice to make between whether to go for adsorption or a simple effusion. Another example, let's take acetic acid plus water mixture. This is a liquid mixture. So here we can do distillation, we can do leaching, we could also do extraction. So for this particular case of acetic acid water mixture, we have a possibility of carrying out distillation, extraction, or so this is not leaching, this should be leaching is for a solid operation. So I meant to say adsorption. Yeah. So you can add a solid adsorbent to selectively remove one of the compounds. Okay. So distillation, adsorption, or extraction. These are the three things that is possible. So now when you look at all these possibilities, mass transfer, mechanical or chemical reaction approach, when you make this choice, the important thing to remember is what is the low cost choice. Okay. So I'll stop here, but if you have any questions we can discuss.